Hello, my name is Gregory Duck and I'm from the National University of Singapore, and today I'll be presenting Binary Rewriting Without Control Flow Recovery. This is joint work with Gao Xiong and Bik Roy Chowdhury, also from the National University of Singapore. So the topic of today's presentation is binary rewriting, and specifically static binary rewriting. For example, suppose that we wish to instrument the highlighted test instruction, which we will refer to as the patch location. Then what we can do is rewrite the binary file into a new binary file where the instrumentation instructions have been directly inserted into the instruction sequence of the original binary. Now when the new binary file is executed, the instrumentation instructions will be executed before the patch location. In general, static binary rewriting is an important problem that has many applications such as instrumentation, repair, and hardening. However, in general, static binary rewriting is considered to be a very difficult problem. One key challenge is that inserting new instructions moves other instructions, and this can change the set of jump targets in the rewritten binary. Unless these jumps are corrected, they will target the wrong address, meaning that the rewritten binary may crash or otherwise misbehave. However, in order to correct the set of jumps, the set of jump targets must be known, meaning that some control flow information must be extracted from the input binary, and this is something that is very difficult to do statically. For example, the jump target may be the result of some arbitrary dynamic calculation, meaning that the problem is undecidable in general. Another problem is that not all jumps will be visible. For example, the jump may reside in a shared library outside of the rewritten binary. For these reasons, most existing static binary rewriting tools suffer from poor scalability and will not work on very large binaries such as Google Chrome or Firefox. Instead of directly inserting instructions, another idea is to replace the patch location instruction with a jump to a trampoline. The trampoline will execute the instrumentation and the displaced instruction before returning control flow back to the main program. This approach has the advantage that it does not move any other instruction, meaning that the set of jump targets from the original binary will be preserved. This also means that we can statically rewrite the original binary without recovering control flow information. However, this basic approach can only be applied if the patch location instruction is the same size as or larger than a jump instruction. If the instruction is too small, this approach cannot be directly applied. So let's consider the problem in reverse. Basically, what we want to do is replace the patch location instruction with some other instruction that will divert control flow to a trampoline. All we need to do is figure out what this replacement instruction could be. In our example, the patch location instruction has a 3-byte machine code representation. However, let's make the problem more challenging by replacing the 3-byte patch location instruction with a single byte instruction. The new instruction will be pop RDX. So now the challenge is to find a new instruction that can replace a single byte instruction and divert control flow to a trampoline. What we can do is we can list all the x86 instructions that can divert control flow. The first instruction, int3, has a single byte machine code representation, so appears to be suitable. However, this instruction diverts control flow using signal handlers, which are too slow for our application. The next sequence of instructions are jumps and calls, and in principle these could be used. However, jumps and calls have a machine code representation of 2 or more bytes, so do not fit into our single byte patch location. The final candidate is the return instruction, which has a single byte representation. However, the return instruction depends on the current value of the stack pointer register, which we have no control over, so this instruction also cannot be used. So based on our analysis, it appears that there is no suitable instruction that can divert control flow to a trampoline. However, surprisingly, there is a method that can be used to divert control flow, even for single byte instructions, and to do so we must consider the machine code representation of the jump instruction. So let us consider the machine code representation of the jump instruction more closely. The jump instruction consists of a single byte opcode, which is E9 in hex, followed by a 4-byte relative offset. This relative offset will be added to the instruction pointer in order to implement the jump. But the important thing here is that the opcode is only a single byte. So let us consider the instruction sequence once more, and suppose that we replace our single byte patch location instruction with the E9 opcode. Next, let us consider what will happen when the CPU executes this modified machine code. As the CPU executes instructions, it will reach the E9 opcode. But because E9 is the opcode for the jump instruction, the CPU will interpret the next 5 bytes as a relative jump. If the corresponding jump target happens to be empty, we can put the trampoline in this location. The trampoline can execute the instrumentation as well as the displaced instruction, before returning control flow back to the next instruction in the original instruction sequence. The rest of the instruction sequence will be executed as normal. This basic approach is known as instruction punning and was first introduced in the PLDI 2017 paper, Instruction Punning, Lightweight Instrumentation for the x86-64. This approach is called instruction punning because some of the bytes of the jump instruction overlap with some of the bytes of the original instruction sequence. In effect, these bytes are punned, meaning that they are used by more than one instruction, which is allowable under the x86 architecture. The main advantage of instruction punning is that it does not move existing instructions, meaning that the set of jump targets in the original binary has been preserved. This also means that we can insert jumps to trampolines without affecting the control flow of the original binary. However, the main disadvantage of instruction punning is coverage. Sometimes, when we attempt to insert a trampoline, the corresponding address will be occupied by some other object, such as program data. If this occurs, the trampoline cannot be inserted and the instruction punning step will fail. So in summary, instruction punning can be used to insert jumps to trampolines for instructions of any size. However, this process is not always reliable, and in the experiments from the paper we found that baseline instruction punning has a coverage of around 77%. This also means that around 20% of all instructions cannot be patched, and that boosting instruction patching coverage is one of the key technical challenges of this work. One idea is to fall back to using signal handlers and interrupts. However, this is quite slow and we want to avoid this as much as possible. Another idea is to patch a different instruction from the same basic block. However, this assumes that basic block information, which is a form of control flow information, is available, which is in violation of our assumptions. Instead, the main technical contribution of our paper is a new set of instruction patching tactics named T1, T2, and T3. These instruction patching tactics are designed to boost the coverage of baseline instruction punning without relying on signal handlers or control flow information. The first instruction patching tactic is T1, otherwise known as padded jumps. The T1 tactic is an extension of baseline instruction punning. In the case of the baseline, we attempt to insert a jump to a trampoline by replacing the patch location instruction with the E9 opcode. This will sometimes fail, leading to poor coverage. However, under the x86, more than one encoding of the jump instruction is possible. For example, the x86 supports several instruction prefixes, such as the rex prefix or segment selector prefixes, and these can pad the size of the jump instruction without affecting its semantics. Each time we insert a new prefix, we get a new address that can be used to host a trampoline. This effectively allows for multiple attempts at instruction punning and can boost coverage to 92% by our experiments. However, this also means that even with the T1 tactic, we still fail to patch around 8% of all instructions, meaning that there is still room for improvement. We can further improve coverage using the T2 instruction patching tactic, otherwise known as successor eviction. Here, the basic idea is to relax the restriction that we do not modify other instructions, provided that the modification does not change the program semantics or affect the set of jump targets. To do so, we will evict the instruction that is the successor to the patch location instruction. This works by replacing the successor instruction with a pun jump to a so-called evictee trampoline. The evictee trampoline simply executes the evicted instruction before returning control flow back to the main program. This does not change the execution semantics of the program, but changes the byte values of the successor instructions, allowing for new puns to be discovered where previously none were available. This tactic boosts coverage slightly to around 94%. However, still around 6% of all instructions cannot be patched. The final tactic is T3, otherwise known as neighbor eviction, and this tactic is designed to boost coverage at the cost of a more complicated setup. The basic idea is that instead of modifying the patch location, we will set up a pun jump inside a neighboring instruction. Next, we will connect the pun jump to a short jump from the patch location, effectively setting up a double jump to the trampoline. However, in the process we have also modified the neighboring instruction. To correct this, we set up another pun jump, this time diverting control flow from the neighbor instruction to an evictee trampoline, similar to the successor eviction tactic. So the result is a very convoluted setup, and is essentially spaghetti code with overlapping instructions. However, the execution semantics and jump targets for all instructions except for the patch location have been preserved. This tactic also boosts coverage to over 99.9% according to our experiments, including the 6% of instructions that could not previously be patched by other tactics. The reason for the high coverage is that the T3 tactic can be applied to any neighboring instruction byte within the short jump distance of the patch location. For a typical application, this translates into around 100 different positions where the T3 tactic could be applied. This means that it is very likely that at least one of these locations can be used for the T3 tactic. So we have implemented our approach in the form of the E9 patch static binary rewriting tool, which is available for download from GitHub. Here is a quick example of what the transformed binary code looks like, where instructions have been replaced by overlapping jumps effectively obfuscating the code. Although the code appears to be obfuscated, the execution semantics and jump targets in the transform binary have been preserved. So here is a quick demo of the E9 patch tool in action. Here we are going to statically rewrite the Google Chrome binary, which is over 100 megabytes in size. Specifically, we are going to instrument all jump instructions, including 2-byte jump instructions, using an instruction counting instrumentation. This works out to be nearly 4 million instructions, and in the end we can see that our tool achieved nearly perfect coverage. Now we can run the modified Chrome binary and it will print instruction count information to the terminal. The modified binary runs as normal, although it runs a bit slower because of the instrumentation. The video here has been sped up to be about twice that of normal. The E9 patch tool has an overhead of around 50 to 100%, but this depends on the application and the number of instructions that are patched. More importantly, because the E9 patch tool does not need to recover control flow information, it can scale to very large binaries including Google Chrome and Firefox. Finally, the E9 patch tool is free and open source and can be downloaded directly from GitHub using the following link. This brings us to the end of the presentation, and I thank you for your attention.